Aristotle, borrowing from Empedocles' elements like fire, earth, air, and water, added a fifth element, quintessence, or the ether, which is what the crystal spheres are made from. Ether is therefore, to Aristotle, a particulate matter which physically fills the universe. This was one of the first, if not the first, non-theological explanation for the nature of the heavens. But this non-theological approach did not last long, as this ether and the crystal spheres would soon be adopted into Christian theology, making changes to it such that those different layers of spheres became different levels of heaven. Outside the taking of this idea, nothing of value in regard to the ether was produced at this time. Investigations into the nature of the universe would not return for almost 1900 years. Nicholas Copernicus, in 1543, published his work On the Revolutions of the Celestial Spheres, in which he presents an entirely different paradigm of the universe. Copernicus questions the nature of Aristotle and the Church's celestial spheres, suggesting instead that it is the Earth that moves. He presents a model where the Earth revolves around the Sun, and rotates about an axis which is tilted relative to the Earth-Sun orbital axis. Part 2. The Matter-Ether and the Principle of Relativity. Copernicus's new model of the universe provides us with an introduction to the principle of relativity, which will be important for the rest of this series. Relativity means that things can appear differently to different observers. The simplest example is to draw a 6 in the sand while someone else stands directly opposite you and your doodled 6. The other observer will see a 9. They can know that you see a 6 and can understand that they too can see a 6 if they perform a rotation of position. Therefore, we can say that the appearance of the digit is relative to the position from which the observer views the symbol. This is the basic conditions of the principle of relativity. Different people can see different things, even opposite perspectives, but all must agree that the perspective is the same if they make the proper physical changes. Copernicus created a greater example of relative observations. Earth, from a stationary position on the Earth, can appear to be stationary itself, while the stars appear to rotate overhead. However, from a position outside of the Earth, like from Mars, it would appear that Mars is stationary, and it was the Earth that was a wandering heavenly body rotating around Mars. A bug, stationary on a spinning ball, would see you revolving around the ball, whereas you see the ball spinning with a bug clinging to its surface. The motion of objects around you can appear to be moving relative to your stationary position, even if it is you who is moving past the stationary object. This idea that the Earth was the one moving was not adopted by others very quickly. One such disbeliever of Copernicus was Tycho Brahe. Brahe was born 3 years after the death of Copernicus. 27 years later, Brahe published his On the New Star, which disagreed with Copernicus that the Earth revolved around the Sun. He believed that the Sun orbited Earth. However, he did believe that the other planets were orbiting the Sun. Brahe also disagreed with Aristotle that the heavens were on-changing, as Brahe's work On the New Star was about a supernova that Brahe observed in the constellation Cassiopeia on November 11, 1572, which instantly disproved the idea that anything beyond the moon was eternally on-changing. Most other viewers of the supernova naturally held that it had been some phenomenon somewhere between the Earth and the moon. So Brahe's observation that this was in fact a change in the outer space brought with it another major paradigm shift. Suddenly, every single object that had ever been discovered in the night sky was not now an eternal, unchanging Platonic form, but rather was a physical object with physical properties, and that the light from these objects had to travel from the stars through the ether. Needless to say, this discovery raised far more questions than it answered. Now, there was research jobs for understanding inner space, studying the planets, the sun, other objects in the solar system, and now outer space, studying the stars and the other heavenly bodies that could only just barely be seen. In 1609, Johannes Kepler published his first two laws of planetary motion, which knocked down another pillar of Aristotle's celestial spheres. Aristotle believed that the planets moved in perfect spheres, but Kepler's observations of the planet Mars led him to the inductive conclusion that all planets have elliptical orbits. This inductive step requires an understanding of geometry, but once one sees the geometry, one will see why it gives Kepler's first law its two results. 1. All planets orbit on ellipses, and 2. The Sun is not located at the center, but at one of the two focal points of the ellipse. A year later, in 1610, Galileo Galilei observed the moons of Jupiter. These heavenly bodies were previously observed, but assumed to be fixed stars near Jupiter, trapped in the crystal ether celestial sphere. Galileo observed that these objects were orbiting Jupiter, eclipsing the planet, then eventually moving behind the planet, then re-emerging and eclipsing it again. Today we call these moons the Galilean moons, and they were given the names Io, Europa, Ganymede, and Callisto. Today, however, we know that Jupiter has far more moons than that, having 79 moons in total. This was strike three for Aristotle, and it led Galileo to question whether other ideas of Aristotle were incorrect, like whether the speed of light was instantaneous, or if it had to travel the ether, taking time to get from one place to another. Despite the shown issues with the Aristotelian model, people struggled to grasp how it could be possible for Earth to be in motion. If Earth was in motion, that might help explain the apparent motion of the stars, but if Earth was in motion, and the distance to the Sun was great, then the Earth had to be moving at great speeds. And if the Earth is moving at great speeds, wouldn't it be the case that jumping straight up into the air should displace you the distance the Earth moved while you were not touching it? Galileo wanted to put an end to this argument, and in 1632 he published the work that would get him in trouble with the Pope, Dialogue Concerning the Two Chief World Systems. This dialogue between Salvati, Segredo, and Simplico was used to demonstrate the Copernican model in full, including answering concerns that the fool Simplico asked. Given that the Pope's views match those of Simplico is one of the reasons that the Church had Galileo put on house arrest. Galileo stated openly in the starting section of his book, "I have taken the Copernican side in the discourse." The dialogues thus present the mathematics and theory behind how the Earth moves and the effects that this cause has on the planet, such as the tides. This book contains within it a thought experiment which Galileo may have actually performed. Galileo's thought experiment placed insects, fish in barrels, dripping water, object tossing, jumping men, and burning candles inside the cabins below the deck of a ship with the windows closed. From inside the ship, on a calm day without external forces acting on the ship, meaning no wind or waves are pushing the ship, it is floating still. The insects fly in every direction, no direction appearing to take any more effort than any other direction. The fish all swim in different directions, without any direction requiring more effort than any other. Water from a container with a slightly open valve drips water straight down into the center of a bowl below it. Objects that are tossed with the same required effort, no matter which direction they are thrown. Jumping straight into the air does not cause you to land in a different location than the spot you had jumped from. And the candle smoke rises in each direction equally, not one direction being more favored than another. If you repeat all of these tests when the ship is sailing at an unchanging velocity, meaning the ship will not accelerate or slow down at any time in its movement, each result will be the same as when the ship was not in motion at all. Galileo concluded, the cause of all these correspondences of effects is the fact that the ship's motion is common to all things contained in it, and to the air also. Galileo concluded then that one inside a closed cabin in a ship cannot tell if the ship is moving at a constant velocity or not moving at all. From this, Galileo concluded that if the Earth is rotating on an axis at a constant velocity, the people of the Earth would not notice, as it is equivalent to not rotating at all. All this is explained with what is called Galilean relativity. Galilean relativity can be mathematically formulated with what is called a Galilean transformation. A Galilean transformation is used to move between two frames of reference mathematically, which only differ by a constant relative motion. An example would be that from the point of view of an observer on shore watching the ship sail past, the observer can see a cannonball that is dropped from the crow's nest will move with the same speed as the ship as it falls. So from the point of view of a person standing still on the shore, the cannonball falls with a curved path. To the crew member dropping the ball from the crow's nest, the ball's forward motion is masked by the ship's motion, and the ball appears to fall straight down. Galileo thus presents us with the idea that two observers in different initial reference frames will agree to the time it takes for the ball to fall to the deck of the ship, and will agree as to where the ball landed, but they must disagree on the path of the ball as it appears to them. To one, it is an irreducible fact that they observe the ball falling down while traveling in a positive x direction, while the other must argue that it is irreducible to them that the ball did not make a positive x direction movement, but rather fell straight down. If you flip this example, and the ship's crew member watches the man on shore drop a ball from a high height, the sailor would see the man moving at a steady velocity in the negative x direction, and he would see the ball fall downward in a negative x direction. The man on the shore would only see the ball fall straight down. This is the principle of relativity. The principle of relativity allows us to assume the equations describing the laws of physics have the same form in all admissible frames of reference. Or otherwise stated, the laws of nature must look the same to one observer as they do to another, and their math ought to work out the same. It is essentially this principle of relativity that allows for all science to be possible, as without this principle we would not be able to assume that experiments done in this laboratory will be valid in the laboratory across the world or across the street. So let us add this principle to our current list of principles. The laws of physics must look the same to one observer as they do to another, meaning there is no physical way to differentiate a body moving at a constant velocity and an immobile body. Let us quickly recap these past events into a new perspective that physicists and philosophers following these intellectual giants would have as their new basis. the universe went from an eternally unchanging state of heavenly perfection, untouchable and unknowable to man, to suddenly an eternally changing state of physical change, causality, and decay, which was just currently untouched by man. The stars figuratively fell from heaven down into the place of mortal men, possible of being created in a lab if understood well enough. Light became an entity that took time to travel from place to place, meaning it had to travel through an entity of perfect transparency. The Earth went from motionless to moving at constant velocities, one rotational velocity about an axis through the Earth, and another velocity of rotation around the Sun. Discovering our place in the universe suddenly became a lot harder to understand, as you cannot even know when you are observing a constant velocity or whether you are observing a stationary object while moving at a constant velocity. With that recap in mind, we continue on to the exploration of the universe, keeping in mind now that future research would be needed in understanding 1. What the ether is made of, and whether it moves or not, and 2. What light is made of, and whether it moves or not. This video is possible thanks to contributions to the Existence University Patreon by viewers like you. Thank you.